Hello students, it's Ms. Mason here, and today we are going to talk about a seismograph. If we are at a seismogram station, so where they produce these seismographs, most of the time it's not feeling any waves, so we just see a straight line, like this. Most of the time, no waves are detected, you're just going to see a flat line. All right, so this is like a EKG or ECG, electrocardiogram, where they record heart rate, and your cardiac waves. When it's flat line, that's not a good thing, the heart's not beating here. All right, but in this case, there are no waves detected on the Earth. Okay? Then, all of a sudden, if we start getting some seismic activity in the form of P waves, could look like this. And then a little later we get waves that start looking like this. Okay, so this is a representation of a seismograph. Okay, so here we have no seismic activity. Here we have our first set of waves, and here we have a second set of waves. These are the seismic waves produced from an earthquake. And we learned about the two types, P waves and S waves. So the ones that come first, these are the P waves, and these are the S waves. The bottom of every seismograph, now we have a seismograph. So what does this mean? Here, where these waves first start, these are all P waves. Remember, P waves come first. Right here is where, gosh, it's not, okay, I need a ruler. Okay, but this is where the P waves arrive. Okay, this is where they arrive at the seismogram. So P wave arrival is this line. Right here. This line is the P wave arrival. P wave arrival. So in other words, that is when this seismogram first detects these P waves right here. 6 a.m. in the morning. So 6 a.m. we're going to say P waves are detected. All right, so these P waves are coming in. And 5 minutes later, we have a different type of wave. These are the S waves. So these are S. Remember, think of snake. Kind of looks like a snake. They're transverse waves. They move a little slower, and they can only actually go through solids. So think of all the S's that relate. So a slithering, slow snake on a solid sidewalk. Okay, so this point then, where we start having these different waves come in, is going to be the S wave arrival. So this point, right here, this line, S wave arrival. This is when the S waves came in. Oops. So this is the time they came in. So that is 6:05. So 6 o'clock we have P waves, 6:05 in the morning we have S waves. The difference between them is called the lag time. So this distance between, so this time between, which is 5 minutes, is the lag time. And remember, we talked about if it's a longer lag time, in other words, you're running on low connection, you've got one bar, you're out hiking out in the Sierras, you don't have much reception. So signals are not really coming in very strong, very fast. If there's a large lag time, the earthquake is far away. On the other hand, if you're Palo Alto and you've got the best internet connection there is, it's faster, it's almost as fast as the speed of light, which isn't really possible to pretend, then the lag time is shorter. That would mean that the earthquake is closer to you. right? So think of it that way, if you think of these waves. Okay, so the lag time is 5 minutes. We're going to take that information now and figure out the distance we are from the epicenter. So remember, the epicenter is above the center. So we're going to try to figure out where this earthquake is located by using a S wave and P wave time graph. Our lag time is 5 minutes. So here we have the earthquake P wave and S wave travel time chart or graph. And what we have to do first is figure out the epicenter distance. So how far away we are from the epicenter if we have a lag time of 5 minutes. So I go down here at 0, 0, right here, and I'm going to create a line going up to 5. That is our lag time. Now I'm going to take that and find where on the graph, or where that would actually fit. So we're looking at where on this graph, and it looks like maybe right there. Now this, so it looks like it fits right there. So what this again shows us, if we just look at the overall graph before we look at this line, is distance and time. So we're looking at really the speed of the P wave and the speed of the S wave. But we want to figure out how far we are from the earthquake with a lag time of 5 minutes. So I'm going to just place this lag time of 5 minutes, so that distance, what that is, find an area on the graph where it's going to fit between S and P, and then I'm going to scroll down to where that lines up to the epicenter distance. Now these are in thousands, so this would be 3,000, this is 4,000, and we have 1, 2, 3, 4, 5. This would be 200, so 3,200, 3,400, 3,600, 3,800, and 4,000. So we're going to say this is 3,800 kilometers away. So that is how we would figure out the epicenter distance. So our epicenter distance for this example is 3,800 kilometers. So now we determined that the epicenter distance is 3,800 kilometers. So now we need to figure out what time this earthquake happened. And to do that, we need to know how long it took for these waves to travel 3,800 kilometers. So what we do then, you can use either P or S wave, and it will make sure it's correct. We start at the epicenter distance. So we go down here to where we were at 3,800 right here. All right, so I'm going to use the P wave. I go up to where it intersects the P wave. Okay, so right here. All right, and then I'm going to go across to determine how long it took that P wave to travel 3,800 kilometers. So we can see these are in minutes. This is 6 minutes. This is 7 minutes. It's divided up into thirds, 60 seconds and a minute, right? So this could be 20 seconds, 40 seconds, and this would be 60. So 6 minutes and 40 seconds would be the travel time. That, in other words, that is how long it took the P wave to travel 3,800 kilometers. And we're going to round that number to 6 minutes. So now we have the epicenter distance, or the distance we are from the earthquake. And that is 3,800 kilometers. So that's how far that earthquake is away from us. And we can use triangulation methods to figure out the exact location of that earthquake. The next thing we were able to figure out is how long it took a P wave to travel. So the P wave was 6 minutes and 40 seconds. We're just going to round it up to 7 minutes. So we're going to say the P wave took 7 minutes to go 3,800 kilometers. We have the seismograph again, just this P wave arrival. So as the first waves detected on the seismograph came in at 6 o'clock. 5 minutes later, the S waves came in, so the lag time was 5 minutes.
Okay.
We put that 5-minute lag time in our S wave and P wave time travel chart, and we were able to determine that the distance from the epicenter is 3,800 kilometers.
Okay.
Once we got that, the 3,800 kilometers, we used that S wave and P wave time travel chart again, and we lined it up with the P wave to figure out how long it would take for that P wave to go 3,800 kilometers.
Okay.
And we figured out that the P wave took 6 minutes and 40 seconds. So we're going to just round it up to 7 minutes. So the distance to the epicenter is 3,800 kilometers. That's the distance. The P wave time travel is 7 minutes. So in other words, it takes the P wave 7 minutes to go 3,800 kilometers. All right, so we could in fact determine the speed, right? Speed is distance over time. But right now we don't have to really look at the speed. We can just look at, we know the distance. That's our distance to the earthquake. And it took 7 minutes to get to us, where the seismograph, the seismogram is. So our first P wave came in at 6 o'clock, and it took 7 minutes to get there. So the question is, what time did the earthquake happen? So what do? We have to work backwards. So if it takes 7 minutes for this P wave to arrive, and it arrived at 6 o'clock,
Okay.
we would just work backwards. P wave arrived 5:53.
Okay.
So the earthquake then occurred at 5:53. So look at what we can get. Look at all this information we can get from just a seismograph. By looking at the seismograph, we can figure out the time the P wave arrived, the time the S wave arrived, and the difference between them is the lag time. We determined the lag time's 5 minutes, so we use that information in that S wave and P wave travel time chart, and we're able to figure out that that meant the distance to the epicenter was 3,800 kilometers. All right, so once we figured out the distance, we could figure out how long it took for these waves to get
Okay.
there, to travel that distance. So we looked at the P wave. You could have looked at the S wave. You could have done both to check in to see if it was correct. When we did that, so again, we used that P wave and S wave time travel chart, and we determined the P wave takes 7 minutes to go the distance of 3,800 kilometers. So that means if our P wave first came in at 6 o'clock, we go backwards, the earthquake would have occurred at 5:53 a.m. So from a seismograph, you can get not only the distance to the epicenter, but you can also get the time the earthquake happened. Now, to get the exact location, we would have to go back and use triangulation. So we would have to take 3 different seismograms and analyze those to determine the distance to the epicenter. And then to create those circles, and where they intersect, that would be the exact location. So, geology rocks. Rocks. Earthquakes rock.